In this video, we are going to talk about example 32, integrations involving and vertical asymptotes within its range of integration. In this case, we will be dealing with an improper integrand of the second kind. In the improper integral of the second kind, the integrand function is not well defined in certain finite values of x within its range of integration. So we have to handle the divergence that occurs in the integrand function while doing the integration. In comparison, we have been dealing with improper integration of the first kind in example 30 and 31. These are improper integral of the first kind. The integrand functions are all defined within the range of integration from some finite term to infinity or from minus infinity to positive infinity. Example 30 and 31 are considered as improper integral in the sense that the values of x has to be taken to infinity. Whereas for the improper integrals of the second kind, the integrations are taken within an finite range of x, but at certain values of finite values of x, the functions of the integrand is not defined. So in this case, we are going to deal with the function of 1 over square root of x. If we choose the finite values of x and trace the values of the function at the point x, the function would become not defined as x is made to tend towards 0 from the right. So the values of the function will just shoot to infinity. As the values of the functions is not defined at the point x equals to 0, but yet we are going to calculate the integrations of the function between the limit of 0 and 1. We have to think of the proper way to handle the infinity that occurs at the point where the function is not defined. So let's see how we are going to handle this improper integration of the second type. Since the function of 1 over square root of x is not well defined at the point x equals to 0, we cannot evaluate the function at x equals to 0 directly. Our purpose is to obtain the area under the curve of this function, which is represented by this integral. In order to evaluate this integral from 0 to 1, we first replace the lower limit of x equals to 0 at which the function of integrand is not defined by a finite value of a, and let a tend towards the values of 0 from the right. Replacements of the lower limit 0 by infinite values of a, which is not 0, will avoid the direct evaluations of the values of the function at the exact point of x equals to 0. The replacement of the lower limit 0 by a finite values of a that is not 0 but larger than 0 is similar in spirit in the case of the improper integral that involve x taken at infinity. In the case of the improper integral of the first kind, we calculate the integrations of the functions at, say, an infinity. In that case, we replace the integration at the infinite upper limit by a finite value of b. After that, we make b to go to infinity. This is a strategy deployed in evaluating improper integrations of the first kind. In the case of the improper integration of the second kind, we do the same tricks by replacing the values of the lower integration where the function is not defined by a. We will take the limit of a going to 0 from the right. By replacing the lower limit integration 0 with a would allows us to be able to evaluate the integral at a point very close to 0 but not exactly 0. To proceed with our calculations, we first evaluate the integral in terms of a. I will first call the capital function fx to represent the indefinite integrations, and that will give me 2 times x to the power of half plus n constant. In the notations of the capital function fx, the proper integrations from a to 1 could then be expressed as the capital function f evaluated at the values of 1 minus f evaluated at the values of a. And that is just 2 multiplied with 1 raised to the power of half, where this is just replacing values of 1 into this expression minus f of a, which is 2 times the a replacing x in this expression, and that will just give me 2 minus 2 square root of a. That finish up the first step. The second step is to then take the limit of the integration in terms of a to 0 from the right. We just copy down the expression of this integral, which has been obtained in the previous step, 2 minus 2 square root of a. Therefore, it is quite straightforward to see that when a is taken to be 0 from the right, that means when a is positive and tends towards 0, this term will just give you 0. Therefore, we end up the limit of these proper integrations is just simply left with the term 2, or this term just goes to 0. So we end up to be 2. Let's tidy up what we have done so far. The integrations of the area under the curve, which is represented by this expression, is represented by y equals to 1 over square root of x. This is x-axis. This is the values of 1. This is the area that is represented by this integration. The area would then turn out to be the limit of dx over square root of x from a to 1, with a tends towards 0 from the right. And this is simply equals to the limit of a tends towards 0 from the right, with this expression for the proper integral 2 minus 2 square root of a, which turns out to be 2. So these integrations, which represent the area under the curve that we are looking for, turns out to have infinite values of 2. So as a conclusion, we have shown for the improper integrations of the second kind, the function to be integrated is 1 over square root of x, and we are asked to find what is the area under the curve for this function bounded between x equals to 0 and 1. The first steps of performing this proper integration is to replace the values of x in which the integrand function is not well defined by a values of a which is larger than 0 but not at 0. We then perform the proper integrations in terms of a as shown here. Then in the second steps, we just take the result of this proper integration in terms of a by setting a goes to 0 from the right. And the result of the limits turns out to be 2. And that is the area under the curve of the function 1 over square root of x bounded between 0 and 1.